Welcome, guys. Happy New Year. Welcome to another video on from Open Delta Tech. Right. So the overview of this lesson will go as follows. We're going to start off with the essentially a basic background of what computer programming is. If you've seen the other videos on fundamentals of computer programming or Python fundamentals, I will cover some of that again. Then we'll talk about briefly what is data, why is it important, and essentially just understanding of data. Then we'll now dive into what is a data structure, why is it important, or why are they important when it comes to computer programming. Why do you hear people talk about how fast is your code? What is the efficiency of your code? What is the speed? How do we measure the efficiency of code? What is the time complexity? Then we'll dive into our first data structure, which is the array. I will talk about what that is and where it's used, the different operations that we can perform on an array, such as search, inserts, and the likes, and their efficiencies. And then we'll finally round it up with just a brief breakdown of what a set is. And yeah, let's get cracking. All right. So overview of computer programming. Let's go. So what do computer programs do? All right. So on the screen, you can see a wide array of applications that are essentially built on top of computer programs. Right on the top left, you see a fighter pilot in his cockpit, and you can essentially see the I guess the controls and the navigation that helps him fly or land. And it looks like he's about to land on a ship, or is either targeting because you can see on the crosshairs over there, he's targeting something, and then you can see the altitude and I think that's the compass, and then the altitude, and then other information that he would use, or she would use, or they would use to essentially fly this big machine, right? So this is a complicated system, but essentially it's all built down, or all built with essentially a computer program, right? And then we move to the right, top right, and we can see a 3D printer, right? So it's a 3D printer. This looks like a CNC machine, but it was supposed to be a 3D printer. Nonetheless, CNC, as you can see, was a laser machine, right? Is the engraving a sheet metal. And as you can see, what essentially happens is you have a computer program that tells the machine what to move, where it is on the X. This will probably be your X, and on the Y, and where it's positioned, and how to essentially draw or imprint what it's supposed to imprint on the sheet metal, right? And you have a computer program that maps out the route that this machine would take to draw that, right? And then on the bottom left, we can see a blockchain exchange or blockchain application. As you can see, there's a transaction of a couple of ETH that's about to happen, right? And we have on this side, we have different, let's see if I can bring out a pen here. What is this? Okay, let's use that. Okay. And as you can, let's bring that back. Great. And then you can see on this side, that's your ETH balance, available balance, and you can see different types of coins or currencies on the exchange, right? So this is all built using a computer program, right? That's just running in the background, and you can see this, and all of this is now brought to life with the creative and engineering aspects of the software developers and the architects that bring this all together, right? And on the right, finally, all we can see is a mobile application and a web application. I'm just showing you like what can be built using computer programs, right? Okay. So what essentially happens is you have a computer that takes in some data, does something, right, in here in this process, right? And then returns either process action data, right, or performs an action. And that is what a computer program, or most computer programs, if not all, are essentially doing, right? So they take in some input, they do something, manipulate that input into some useful information or action, and they return that. And all of that has been done or is being done by people who architect, or who design and build the program, right? That tell the program what to do when it receives this information. Okay. So what is data, right? So you can think of data as a collection of any sequence or symbols, or any sequence of symbols, right? Or facts that can be interpreted and processed by the computer, right? Usually words, numbers, or any other type of useful information, right? That can be processed by a computer, right? So what the computer does, it takes that information, takes that data, raw data, and turns it into something that we deem useful, right? And then, now in this day and age, we have things like machine learning, that essentially is driving the digital transformation that we see across industries. And all of that is based on this big data, essentially, which is what is called a large amount of data that is in different formats and is rapidly generated, right? And then you have these algorithms or the systems that can now process this humongous amounts of data, if I can use that, and then turns it into useful insights or actions that can assist us with decision making, or can create new systems that simplify the way that we've been doing things, right? Different types of data. We have unstructured data, which is what we come across in our day-to-day lives, right? You have your emails, you have your text data, you have your images, you have your videos, right? It's any sort of data that isn't stored in a structured format, right? I know it's a kind of a circular definition right there, but in a structured format, where I mean that there's not a strict relationship between how the data is stored, as you would find out in structured data, which is the traditional way of holding data, where you have data in either a database system, and the tables or the data that's stored have a strict relationship that define how the data is related to other tables, right? And then you can have semi-structured data, which is essentially the in-between these two, right? And then we have metadata, which is just data that describes types of data. And all of this, right, can either be condensed back to a sequence of numbers and strings, right? So that's just a brief overview of what data is, why it's important, why we're talking about it so much these days. And then what are data structures, right? So a data structure are simply the format in which we put together data in a computer program, right? So remember from the first slide, we had the data coming into the program or into the computer so that it can make some action, right? And spit out some useful information or perform some useful action, right? Now, the way that we structure the data, right, can improve the speed at which the computer can generate useful responses or provide a useful action, right? So essentially what I'll be talking about here is the way that we structure this data so that we can have efficient programs, right? So that's kind of the importance of why we're talking about data structures in this video, right? So think of this example where you have a string, right? So there's a string A, string B, and string C. Then we've defined these three variables and they are all of the type string. This is a Python program. And now we want to return this, right, to the command to the output, right? And then we're going to use this function, the print function, that just combines these three string or these three variables, and then returns a sentence, a meaningful sentence that we can use, right? So that is just an example of how we've structured this data. This is just a string format, and then we've put it together, right? So this is just a dummy example, if I can say that. But as we move on, we'll see we'll see the real value of ensuring that you use the right data structures for your computer program. Right. So now if we come back to, or if we look at it from an engineering perspective, right, on data structures. So I say an engineer's perspective on data structures. I have a background in mechanical engineering, so I just want to, from an engineer's side, let's just look at how we would consider the importance, or why data structures are important, right? So if you've ever done a finite element analysis simulation on a component that you were designing, you'd see this type of graph, or this type of plot, not a graph, but this type of plot. And as you can see, right, this is a bike pedal, right? And then we can see on this side over here, if I can start annotating, yeah, let's see if that works. If I circle over that, you can see some constraints, right? So you think of your bike pedal. If you've ever ridden a bike before, you know that your bike pedal is fixed onto I guess, anyway, it's fixed onto the pedal, right? Okay, let me not say it's fixed onto the pedal, but it's fixed onto a fixture where that allows you to rest your foot and propel your bicycle forward, right? And then what we have there on this side of on this axis, as you can see here, you can see this downward forces, which represents the force that you would apply as you cycle, right? And what you can see, this is a displacement plot, right? That shows you the amount of displacement that would happen, right? When you are using your bicycle. As you can see, much as expected. You can see this is at this point is the highest amount of displacement that occurs. And as you go in further into closer to the closest where it's constrained, you can see that the displacement goes away. And if we were to draw this on a 2D plane, right, you would see that, okay, this would now be something like a uniformly distributed load, right? And then, you know, and then you would have like, you can see that you would have some sort of bending moment over here, right? Happening, right? So if this is a uniformly distributed load, if I should be more accurate, you would see that it would come in somewhere like that, right? So this would be the resultant load, and you would have a bending moment across that. And then you can see that at this point, you would have some bending that would occur, and this would where you'd expect the maximum displacement should occur. Yeah, displacement, because looks something like that, if I'm not mistaken. Okay, so now, right, so what happens here? What's the purpose of this plot, right? So essentially, you've designed your load. Now you want to see whether the material that you've chosen, right, is essentially can withstand the load that this component would endure during working operations, right? So now, if I can exit this and then move to this side, right? We've all seen this screen happening, or this pop up on a screen on an application. Maybe you're dealing with a web application or mobile application, but you all encountered where the screen is loading, right? So essentially, where I'm coming from is like sometimes this could be due to a bandwidth issue in terms of the network, right? The network is a bit slow, or it could be that the way that the program has been designed, the data structures used, right, was not efficient enough in terms to be able to distribute the load that is coming from maybe multiple users, or the amount of data that is required to be loaded into memory for it to perform an action, right? So that is why it is important for us to be able to understand data structures when it comes to creating good and production-ready software programs, right? So if I can just, oh, okay, let me see if I can clear all the drawings. Great. So now we move to a table where I just summarize, right? So this is, I'm just going to give you certain aspects of what we look at when we're talking about data structures from an engineer's perspective, and we look at the example of a beam design and thinking about comparing that to a data structure design, right? So the purpose of this, right? So what is the purpose of us doing when we are engineers and we have to design a beam? What you would know that the purpose of you doing this is essentially to ensure that what you're designing is really sound, that, you know, once it's now in production or it's now being used, and then the loads are being applied to this structural member, it does not break and does not lead to catastrophic disaster or lead to death, right? When it comes to data structures, think of it as like the efficient organization of how the data that your program is going to use, so that you can perform fast and essentially reliable operations where you can avoid that loading screen and people don't walk away from you or leave your application because it's taking too long to respond. Then we talk about optimization, right? So when you're designing your structural member, right, you now have to start thinking about costs, right? When we start thinking about the optimization, essentially we're thinking about cost. Do I need to design a 1 meter by 1 meter cross profile, or can I reduce the cross profile, the amount of material that I need, by selecting a stronger material that I don't have to I guess, buttress or compensate with size? I can use a smaller material, and because of its material properties, it can withstand the load. And then I can also save on costs. So you now look at that when you now start selecting your material, the size or the, I guess, the strength required, and also the durability in terms of the lifespan of this material and in terms of when it's being used. Now that also relates back to your optimal data structure choice, goes back to speed and efficiency, right? You don't want your systems to be overloaded, right? So which can lead to like malfunction in in your maybe your data servers, or crashing, you know, when they crash all the time, and then people will like leave your application again. Um, think about stress points, right? This is what we also do in beam design as well. We want to identify the weakest points of failure, right, due to the stress points, or where the highest points of stress, the stress concentrations, and then you want to ensure that you reduce it, either by, you know, if you're if you're in a strength of materials class, or you're in a civil engineering class, you would always know that you wouldn't want a 90-degree angle there, when because that becomes like a stress razor. So you'd want to chamfer that out, or what's the word now? Create a radius. I've forgotten what it's called now. But you want to essentially create a radius to reduce the amount of stress concentration at that point, right? Great. And then also you also want to do that when it comes to your systems, right? In your software systems, so that you can identify where the bottlenecks are happening, so that they don't slow down the application or cause your system to crash, or to short circuit, if I'm not mistaken. Cool. So let's move on. Let's see if I can continue. Scalability, right, as well. So here's some of the important aspects that you want to be looking at, right? So you have scalability, which is always important when you design for, are you designing for, like, let's say you start off as a small startup and you're seeing your user base grow exponentially, right? For maybe 50 users to like 1 million, hopefully. And that's always good to have 1 million users using your application or using your solution. But you have to ensure that stress from 1 million users on your software does not break down your application, right? And that leads to poor user experience, right? Then you also want to talk about performance measurements, right? So this is what we essentially will be doing in this series. We'll be looking at the time complexity of operations when we come to our software programs. Okay. Okay, and then this is not under various LADs, but under various loads, right? Great. And let me just clear this again. Clear all drawings. So now we go to the array, right? And move that again. So the array is a fundamental data structure, right? You'll come across it in all programming languages, right? But here we'll be dealing mostly with Python, and in Python, the array is referred to as a list. But let's continue. So an array is essentially a collection of various items. And then you can have different types of arrays, but we'll keep it simple. So, right, you have an array of numbers, right? And these are the values in this array, right? And then the array are how to access these values. We use the index, right? The index position of the array, right? And in most programming languages, the index starts counting at 0, right? And then as you move towards the right, increases. So in this one, we have an array with 6 values. So the first value would be index 0, and then would get to index 5, right? And how would you access that? That essentially the computer would come and look at the memory location of this array, of this index 0, and based on that, it will be able to get to 5, because it's essentially a sequential increase in the memory location at 0. So 1 plus, but I'll show you that now. So an array index maps to the position within the array, like I just mentioned. So if this was index 1, we would know that it's the second value in our array, right? And here are the operations that can be performed in an array. We can read a value, right? So if I wanted to know the value at index 4 of this array, I'll be able to just go to, computer will be able to go to index 0, right? It knows the memory location of this index 0, and we saying it's 4 places away. So 1, 2, 4, which would be 5 places away. So 1, 2, 3, 4, 5. Or we can say 4 from 0, 1, 2, 3, 4, right? And then it'll just take that, right? So that's the read operation. And then we have the search operation. So we can say, does this array have the value 55, right? So it'll go to index 0. Is this 55? No. Let's go to index 1. Is this 55? No. Is this 55? No. Is this 55? No. Is this 55? Yes. And then it will say that it has 55 in this array, and then it probably return it to you. And then we have the insert value. We could say, I want to insert the value 180 into this array. So I could either add it, in fact, I could add it anywhere. I could add it here, and then, we'll get into the nitty-gritties of how that is done. And then we have the delete, where we could actually say, you know what, I don't want number 234, and let me remove it from this array. Okay, so let's think of, so we have a savvy investor who's looking at a stock market of cryptocurrencies and wants to look at what he should buy, right? Because the market is looking good. So he goes to all the available, he checks for what are the available stocks on Open Delta Exchange, right? So here's what the computer will do. If this was a software program that we can see over there. So it's going to go in and it's going to go to memory location that has all the available stocks. So we've saved all the available stocks to an array, right? And then it's going to read and return the value stored in the memory location, right? So it's going to say, okay, so in the available stocks array, we have Microsoft, Apple, Google, Bitcoin, and Ethereum, and Fetch AI. Those are the available stocks. And then let's look at the read operation, right? So what we want to do here is to look up at a specific value at specific index of an array, right? And then so it's going to take one step. It takes one step to do that because let's look at this computer memory. This is what a computer memory would look like, right? We have our array right there. And then in other locations, we have values, different values, right? And I say it takes, it is a constant, I'll explain. So this is the big O notation, but essentially this is essentially saying that it's a constant, it takes it's a constant operation, right? When I say constant, takes the number of operations that it takes is constant. It's not a function of the number of data items, right? That it's operating on. I hope that makes sense. We'll get into that. So this is our computer memory, and then these are the memory locations. So that's how it's doing that. So this is 2006 up to 2030. So it can just jump to memory location number 2011, and then it would know what is there. And from then on, it's just a sequential movement of finding the values that are in at these locations, right? So when you're creating an array, what essentially you need to find a location that has, let's say you have 5 values. You have to get a location on your computer memory of addresses or location and look for the place where it can place those 5 values, right? So you can, most times you can't place one value here, one value there, or one value there. And this, we're going to build it up from here. They just say we're going to look for a location that is free for the 5 values to take. Okay. So here is memory location 2011, and then we store Microsoft there, and then from then onwards, we're going to store the remaining, and this is our array. Okay, so now we have the search operation. Now we want to determine if a value exists in an array and at what location, right? So we want to check, is XRP listed on Open Delta Exchange? Very important. So we're going to look. So this is our array, but we can see that XRP is not here, but the computer can't. Right? The computer is going to go index 0. It's going to go to the available stocks array. I'm going to look index 0. Is this XRP? Nope. 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 And XRP is not listed, right? So here's the algorithm that it would follow. It'll start. It'll read the value at the memory location, right? Is this the value of interest? No, right? So is this the last index? No. So let's move to the next index, and then we continue on that same process. However, if we found it, it'll just store that index and say, yes, this value exists there at this index, and that's the end of that, right? So that worst case scenario of this happening, right? Value is at the end or not in array, right? So you just like we just did right now, we had to go to the very end for it to determine that the value was not in the array. And it'll take n number of checks, right? So that means how many number of items are in that array. In this scenario, there were 6, so it took 6 operations to determine that XRP was not there. So the best scenario of this would be the value was actually at index 0, right? And then we just say, oh, just 1. And then we'll get, but that'll be just 1 check, right? So now we have the index insert operation, right? So we didn't have fetch AI. So, but now we want to put, we didn't have XRP, but now we want to put it in our array. So we want to add a value to a specific index, which is the last index here in this one. And the operation efficiency essentially depends on where we're going to insert. Are we going to insert in the beginning? We're going to insert somewhere in the array as well, or we're going to insert somewhere at the end of the array, right? So the best case, just like the read, is at the end. Why? Unlike the read, I should say, unlike the search, I should say, because the worst case was at the end. It only takes 1 operation because we already know this is the memory address for the start. This is how many items are there. So we just need to go to the last item and just place it there. That just takes 1 operation to do that. We just insert at the end. Right. So now we're going to say, let's insert XRP at index 2. Right. So we must remember that we have to ensure that there's enough space here, right? For this value to be able to be placed in 6. So this side is empty. So we want to put XRP at index 2. Why? It's just for an example, but let's go on. So what we're going to do is going to shift FHAI to that empty position. So this place becomes empty. We're going to switch Ethereum, going to Bitcoin, Google again, and then bam, we've added in XRP, right? So that took us 4 shift operations, 1, 2, 3, 4, and then the insert. So that was 5, right? Now the worst case scenario would be at 0. So what would happen if we're inserting it at the beginning, right? So we'd have to shift all of the items by 1, and then we'd insert. So it would perform n operations because they're n items there plus the insert itself, right? So that's where the n plus 1 comes in. Okay, so this is that. We're going to show you that. So we shift that one there, we shift that one, shift that one, we shift that one, we shift that one, shift that, and bam, there we go, right? 1, 2, 3. Now we have 7 because this is index 6. Right. So that's the worst case scenario, right? Now we have the delete operation, right? So eliminating a value, this is essentially at a specific index. We want to delete fetch AI. Best case scenario is we just have to delete at the end. It just takes one step, right? So let's try and do eliminating a value at a specific index. So let's go remove Google, right? So we've deleted Google, so that's one operation. Now we can't allow spaces in between our array, so we have to shift them back. Shift, 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 right? So that was 1, 2, 3. All right. Worst case scenario, that is going to be the delete at the start. Why? Because remember, we're going to have to shift everything back, right? So we delete that. Step 1, step 2. Step 1 was the delete. Now we have to shift, 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 shift. Right? Now we're fine. Okay. And then the total number of operations is n, right? Because we removed one, and then remember it's 1 plus n minus 1 cancels out, so just left with n. Okay. Now we have the set, which is the unique arrays, right? So what a set is essentially, it wouldn't, as similar to, in this, we're looking at the ones that are similar to an array. It does not allow you to store duplicate values, right? In this scenario, we have two indexes that have the value of Bitcoin. It would not allow you to do that, right? So you have the same type of operations as an array, which is the read, the search, and insertion and deletion, right? However, the insertion and deletion are a bit different, all right? Actually, it's only the insertion. Insertion, okay, I'll explain why this one, the insertion is a bit different, right? So here we want to insert at USDC, right, at the end. Remember, before, the insertion at the end was, the most efficient. But here, what happens is, because we have to now check, it doesn't allow duplicate values. So we have to now check, we want to insert USDC. So the computer has to check, is USDC in index 0? No. Is it in? No. Is it here? No. Is it here? No. Now we can add, right? So that's n plus 1 plus n plus 1 operations. However, if it was in the beginning, right, we would have to do 1, 2, 3, 4, yeah, like we did, which is n plus 1. However, now we need to shift, which is n, so that will become 2 plus n, 2 plus n plus 1, 2n, sorry, plus 1, right? So that is why the insertion is already in red, because the rest are similar, the same. The efficiency is the same, except for the insertion, which is a bit more inefficient, not as efficient, excuse me, not as efficient as the insertion for an array. Okay, I think that's the last slide. Thank you for watching, and we'll be getting back to the next episode where we'll talk more about data structures and how to measure their efficiency. We'll show you some different types of algorithms using Python. So join me on this journey on how to become more, I guess, professional or professional software developer, or developing software applications using an engineering standpoint in terms of ensuring that your system is safe, safe and efficient and fast, using the techniques and science of efficiency measurements and time complexities of your operation. Thank you, and see you in the next episode. Cheers.